Nuclear weapon designs are physical, chemical, and engineering arrangements that cause the physics package of a nuclear weapon to detonate. There are three existing basic design types. In most existing designs, the explosive energy of deployed devices is derived primarily from nuclear fission, not fusion. Pure fission weapons were the first nuclear weapons built and have so far been the only type ever used in warfare. The active material is fissile uranium or plutonium, explosively assembled into a chain-reacting critical mass by one of two methods. Gun assembly. One piece of fissile uranium is fired at a fissile uranium target at the end of the weapon, similar to firing a bullet down a gun barrel, achieving critical mass when combined. Implosion. A fissile mass of either material is surrounded by high explosives that compress the mass, resulting in criticality. The implosion method can use either uranium or plutonium as fuel. The gun method only uses uranium. Plutonium is considered impractical for the gun method because of early triggering due to Pu-240 contamination and due to its time constant for prompt critical fission being much shorter than that of U-235. Boosted fission weapons improve on the implosion design. The high pressure and temperature environment at the center of an exploding fission weapon compresses and heats a mixture of tritium and deuterium gas. The hydrogen fuses to form helium and free neutrons. The energy released from this fusion reaction is relatively negligible, but each neutron starts a new fission chain reaction, speeding up the fission and greatly reducing the amount of fissile material that would otherwise be wasted when expansion of the fissile material stops the chain reaction. Boosting can more than double the weapon's fission energy release. Staged thermonuclear weapons are essentially a chain of fusion-boosted fission weapons, usually with only two stages in the chain. The secondary stage is imploded by X-ray energy from the first stage, called the primary. This radiation implosion is much more effective than the high explosive implosion of the primary. Consequently, the secondary can be many times more powerful than the primary, without being bigger. The secondary can be designed to maximize fusion energy release, but in most designs fusion is employed only to drive or enhance fission, as it is in the primary. More stages could be added and conceptual designs incorporating up to 7 have been produced, but the result would be a multi-megaton weapon too powerful to serve any plausible purpose. Pure fusion weapons have not been invented. Such weapons, though, would produce far less radioactive fallout than current designs, although they would release huge amounts of neutrons. Pure fission weapons historically have been the first type to be built by a nation-state. Large industrial states with well-developed nuclear arsenals have two-stage thermonuclear weapons, which are the most compact, scalable, and cost-effective option once the necessary industrial infrastructure is built. Most known innovations in nuclear weapon design originated in the United States. Although some were later developed independently by other states, the following descriptions feature U.S. designs. In early news accounts, pure fission weapons were called atomic bombs or A-bombs, a misnomer since the energy comes only from the nucleus of the atom. Weapons involving fusion were called hydrogen bombs or H-bombs, also a misnomer since their energy comes mostly from fission. Insiders favored the terms nuclear and thermonuclear, respectively. The term thermonuclear refers to the high temperatures required to initiate fusion. It ignores the equally important factor of pressure, which was considered secret at the time the term became current. Many nuclear weapon terms are similarly inaccurate because of their origin in a classified environment. Nuclear reactions. Nuclear fission splits heavier atoms to form lighter atoms. Nuclear fusion bonds together lighter atoms to form heavier atoms. Both reactions generate roughly 1 million times more energy than comparable chemical reactions. making nuclear bombs a million times more powerful than non-nuclear bombs, which a French patent claimed in May 1939. In some ways, fission and fusion are opposite and complementary reactions, but the particulars are unique for each. To understand how nuclear weapons are designed, it is useful to know the important similarities and differences between fission and fusion. The following explanation uses rounded numbers and approximations. Fission: when a free neutron hits the nucleus of a fissile atom like uranium-235, the uranium splits into two smaller atoms called fission fragments, plus more neutrons. Fission can be self-sustaining because it produces more neutrons of the speed required to cause new fissions. The U-235 nucleus can split in dozens of ways, provided the atomic numbers add up to 92 and the atomic weights add to 236. The following equation shows one possible split, namely into strontium-95, xenon-139, and 2 neutrons, plus energy. The immediate energy release per atom is about 180 million electronvolts, i.e., 74 terajoules per kilogram. Only 7% of this is gamma radiation and kinetic energy of fission neutrons. The remaining 93% is kinetic energy of the charged fission fragments, flying away from each other mutually repelled by the positive charge of their protons. This initial kinetic energy is 67 terajoules per kilogram, imparting an initial speed of about 12,000 kilometers per second. The charged fragment's high electric charge causes many inelastic collisions with nearby nuclei, and these fragments remain trapped inside the bomb's uranium pit and tamper until their motion is converted into heat. This takes about a millionth of a second, by which time the core and tamper of the bomb have expanded to plasma several meters in diameter with a temperature of tens of millions of degrees Celsius. This is hot enough to emit black-body radiation in the X-ray spectrum. These X-rays are absorbed by the surrounding air, producing the fireball and blast of a nuclear explosion. Most fission products have too many neutrons to be stable, so they are radioactive by beta decay, converting neutrons into protons by throwing off beta particles and gamma rays. Their half-lives range from milliseconds to about 200,000 years. Many decay into isotopes that are themselves radioactive, so from 1 to 6 decays may be required to reach stability. In reactors, the radioactive products are the nuclear waste in spent fuel. In bombs, they become radioactive fallout, both local and global. Meanwhile, inside the exploding bomb, the free neutrons released by fission carry away about 3% of the initial fission energy. Neutron kinetic energy adds to the blast energy of a bomb, but not as effectively as the energy from charged fragments, since neutrons are not slowed as quickly. The main contribution of fission neutrons to the bomb's power is the initiation of other fissions. Over half of the neutrons escape the bomb core, but the rest strike nearby U-235 nuclei, causing them to fission in an exponentially growing chain reaction. Starting from one atom, the number of fissions can theoretically double 100 times in a microsecond, which could consume all uranium or plutonium up to hundreds of tons by the 100th link in the chain. In practice, bombs do not contain hundreds of tons of uranium or plutonium. Instead, typically the core of the weapon contains only about 5 kilograms of plutonium, of which only 2 to 2.5 kilograms, representing 40 to 50 kilotons of energy, undergoes fission before the core blows itself apart. Holding an exploding bomb together is the greatest challenge of fission weapon design. The heat of fission rapidly expands the fission core, spreading apart the target nuclei and making space for the neutrons to escape without being captured. The chain reaction stops. Materials which can sustain a chain reaction are called fissile. The two fissile materials used in nuclear weapons are U-235, also known as highly enriched uranium, or alloy meaning Oak Ridge alloy, or 25, and Pu-239, also known as plutonium, or 49. Uranium's most common isotope, U-238, is fissionable but not fissile. Its aliases include natural or unenriched uranium, depleted uranium, tube alloy, and 28. It cannot sustain a chain reaction, because its own fission neutrons are not powerful enough to cause more U-238 fission. The neutrons released by fusion will fission U-238. This U-238 fission reaction produces most of the energy in a typical two-stage thermonuclear weapon. Fusion produces neutrons which dissipate energy from the reaction. In weapons, the most important fusion reaction is called the DT reaction. Using the heat and pressure of fission, hydrogen-2, or deuterium, fuses with hydrogen-3, or tritium, to form helium-4 plus 1 neutron and energy. The total energy output, 17.6 MeV, is 1/10 of that with fission, but the ingredients are only 1/50 as massive, so the energy output per unit mass is greater. In this fusion reaction 80% of the energy, or 14 MeV, is in the motion of the neutron which, having no electric charge and being almost as massive as the hydrogen nuclei that created it, can escape the scene without leaving its energy behind to help sustain the reaction, or to generate X-rays for blast and fire. The only practical way to capture most of the fusion energy is to trap the neutrons inside a massive bottle of heavy material such as lead, uranium, or plutonium. If the 14 MeV neutron is captured by uranium or plutonium, the result is fission and the release of 180 MeV of fission energy, multiplying the energy output tenfold. Fission is thus necessary to start fusion, helps to sustain fusion, and captures and multiplies the energy released in fusion neutrons. In the case of a neutron bomb, the last mentioned does not apply since the escape of neutrons is the objective. Tritium production. A third important nuclear reaction is the one that creates tritium, essential to the type of fusion used in weapons. Tritium, or hydrogen-3, is made by bombarding lithium-6 with a neutron. This neutron bombardment will cause the lithium-6 nucleus to fission, producing helium-4 plus tritium and energy. A nuclear reactor is necessary to provide the neutrons if the tritium is to be provided before the weapon is used. The industrial-scale conversion of lithium-6 to tritium is very similar to the conversion of uranium-238 into plutonium-239. In both cases, the feed material is placed inside a nuclear reactor and removed for processing after a period of time. Alternatively, neutrons from earlier stage fusion reactions can be used to fission lithium-6 and form tritium during detonation. This approach reduces the amount of tritium-based fuel in a weapon. The fission of one plutonium atom releases 10 times more total energy than the fusion of one tritium atom. For this reason, tritium is included in nuclear weapon components only when it causes more fission than its production sacrifices. Namely in the case of fusion-boosted fission. Of the four basic types of nuclear weapon, the first, pure fission, uses the first of the three nuclear reactions above. The second, fusion-boosted fission, uses the first two. The third, two-stage thermonuclear, uses all three.